Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're working examples of beams that have axial loads. In this video, we'll conclude the example that we started in the last two videos. We're asked to evaluate the stresses at point H and K, which are 0.9 meters from the bottom of the member, and the axial force at that location is 20.83 kilonewtons. The bending moment is 7.2 kilonewton meters acting in the direction that I have shown here. My equation for total normal stress is equal to F over A minus My over I. My section properties I can compute knowing that it's a pipe section with an outer diameter D equals 125 millimeters and an inner diameter, small d, equal to 109 millimeters. The area would be computed as pi over 4 times big D squared minus little d squared, where I take 125 squared minus 109 squared, and that computes to 2940.5 millimeters squared. The moment of inertia, the bending moment of inertia, is the polar moment of inertia divided by 2. We'll use this result without proof here, which is equal to pi over 64 times d, big D to the fourth minus little d to the fourth, which computes to 5.055 times 10 to the sixth millimeters to the fourth. And finally, the y value that we'd want to use in the moment equation is equal to half of the outer diameter, or 62.5 millimeters. Okay, so next I'll compute the value of the axial stress and the bending stress. The axial component, sigma axial, equals F over A, equals 20.83 kilonewtons times 10 to the third to convert to newtons, divided by the area, 2940.5 millimeters squared, gives us an axial force of 7.085 megapascals. Or sorry, an axial stress, sigma axial, 7.085 megapascals. The contribution due to bending equal to I'll say MC over I, so I'm using the distance C to the outer reaches of the section, is equal to the moment, 7.2, times 10 to the sixth to convert from kilonewton meters to newton millimeters, times the C value, 62.5 millimeters, divided by the moment of inertia, 5.055 times 10 to the sixth millimeters to the fourth, which computes to 89.02 megapascals. Finally, we put this together on the last slide. Note that the approach that I encourage you to take is to compute the value of each term, the absolute value of each term, which we just did, and figure out the signs by inspection. Okay, so let's start with sigma h. The axial force is compressive anywhere, so this term is going to be negative. So we had negative 7.085. The bending term, on this side, the bending stress, since it's bending in this direction, we're going to have tension on the H side of the member. Another way to think of it is that the load pulling on that side of the member is going to cause the member to curve in that direction, and therefore tension on the H side of the member. So this bending term will be positive 89.02 megapascals, and the result, the sum of those two, is 81.94 megapascals and in tension. That's sigma h. Sigma k on the other side of the member, the axial force term is still negative, But this time the bending term is also negative. This is the compression side of the member. So minus 89.02 megapascals, and those two sum to negative 96.11 megapascals, which is in compression. And that's the result. You can see the result makes sense. We can visualize the beam bending in that direction. We know we're going to have tension on the H side, compression on the K side. Notice that the value for the bending stress, the contribution of the stress due to bending, is much larger than the contribution due to axial force, and this is very typical. This completes this video.